Welcome students. In the previous chapter in electricity, we have discussed about the heating effects of current. Today, we will discuss another effect of current that is called magnetic effects of current. Before we discuss the magnetic effects of current, we should know what's magnet and what are its properties. What basically a natural magnet is. You know, when we study about the magnets, that means we are talking about the natural magnet, which are naturally occurring magnets. So, if we see this magnet has its chemical formula Fe3O4, and its chemical name is magnetite. So natural magnet is an ore of an iron, oxide of an iron, having chemical formula, structural formula Fe3O4, and its chemical name is magnetite. So far the name is concerned, this name has been originated from its place where it has been discovered firstly. And that place was in Turkey. That place was called as Magnesia. So the place where it is discovered first time, that is called Magnesia. This place is in Turkey, and this is why this oxide of iron is called as magnetite, and its chemical formula is Fe3O4. You know, the natural magnet has certain properties. The first important property, you know, that it has a property that it attracts the different magnetic materials towards itself. Like iron, it attracts them towards itself, and that means it attracts the magnetic materials towards itself. And if we see its properties, the first important property of a permanent magnet or a natural magnet is that if we suspend any magnet freely under the influence of gravity, we find that this magnet always rests in a north-south direction. The magnet always rests in a north-south direction. Why? Because Earth also acts as a big magnet. So when a bar magnet is suspended, when a natural magnet is suspended, it always rests in a north-south direction. The first important property that the magnet always rests in north-south direction. So this is the first important property of a magnet. Now the second important property that we call as law of magnets. That law of magnets is that the like poles of the magnet, second important property, the like poles of the magnet, like north pole of one magnet and north pole of the second magnet, south pole of one magnet and south pole of the second magnet. That means like poles always repel. Like poles always repel, while as unlike poles of magnet always attracts. Always attracts. So this is the second important property. The first important property, I will repeat, the first important property is that the magnet, when suspended freely, it always rests in a north-south direction. And second important property is that if we bring two magnets together, and if their like poles are towards each other, they will repel, or if they are placed close together and their opposite poles are bring together, they will attract. So we can say this property that the like poles of magnets always repel, while as unlike poles of the magnet always attracts. The third important property, the most important property of the magnets. You know, the magnet has two poles, north pole and south pole. If we want to separate these poles, there is no possibility of separating these two poles. So there is no chance, we can say there is no way to separate two poles of the magnet. So we cannot separate the poles of a magnet. So third important property is that we cannot separate the poles of the magnet. We cannot separate the poles of the magnet. So why cannot we separate the poles of the magnet? Because the polarity where we break the magnet, for example, if we break this magnet at the center what will happen? At where we break it, that area becomes south and its opposite side becomes north. So these two pieces becomes two separate magnets. So as we go on, if we break this magnet further, again the poles will appear. So we can say a smaller piece of a magnet can have its own north pole and south pole. So that acts as an independent magnet. We can say we cannot separate the poles of a permanent magnet. The magnetic properties. So for the magnetic properties of a permanent or natural magnet is concerned, it is permanent. So we cannot increase the magnetic properties of a permanent magnet, but we can a little bit decrease its magnetic properties. Like for example, if we take a magnetic property of a bar magnet, it has a constant magnetic properties. This bar magnet has a constant magnetic properties. We cannot increase its magnetic property. If we want to increase its magnetic strength, we cannot. But we can decrease its magnetic strength by throwing, by hammering, by giving heat, or by giving electric shocks. So the magnetic properties, the magnetic strength of a permanent magnet cannot be increased. But we can decrease its magnetic properties, magnetic strength. How can we decrease its magnetic strength? The number one, the first important step is by throwing, or rather we can say by hammering. By hammering. If we hammer permanent magnet, what will happen? The domains of that magnet get disturbed, so its magnetic strength will disturb. Number one. Number two, if we heat the magnet by giving heat, what will happen? The domains inside, the tiny magnets inside, they will rearrange itself, or they will change their positions. So we can say the second important factor which decreases the magnetic strength is heat, by giving heat. And the third important factor is by giving electricity. By giving electricity, or by giving electric shocks. If we provide electric shocks to a permanent magnet, that permanent magnet loses completely its magnetic strength. So we can decrease magnetic strength of a permanent magnet, but we cannot increase its magnetic strength. Its magnetic strength is always constant. So these are certain important properties of a magnet, and its chemical name, its chemical formula, and important properties. Okay. Okay, now let us take the topic, basic topic, that is the magnetic effects of current. You know, students, these all effects which we have discussed from the electricity chapter, like we have discussed heating effects of current there, we have discussed chemical effects, that a general idea of chemical effects of current, and the third is the magnetic effects of current. What is basically magnetic effects of current? It means that the magnetism and electricity, these are interrelated to each other. That means they show a relationship. They are interrelated. And this concept was firstly given by 1820. This concept was given by 1820 by a great physicist named as Hans Christian Ørsted. This person was the main physicist who provide a relationship, who provide a concept of interrelationship between electricity and magnetism in 1820. According to Hans Christian Ørsted, he says that when a current is flowing through a conductor, when a current is flowing through a conductor, that conductor behaves as a magnet. That conductor behaves as a magnet. So we can say, if we generalize this statement, we can say that electricity, by passing electricity through any conductor, the magnetism is produced in that conductor. Rather, we can say the magnetic properties are produced when a current is flowing through the conductor, and this effect was known as magnetic effects of current. That is, it is the effect of current that produces magnetic effects in the conductor. So this is why we call it as a magnetic effects of current. This effect is only possible when current is flowing through the conductor. And this was discovered in 1820 by Hans Christian Ørsted, a great physicist. So according to him, that means if we elaborate or if we discuss this statement further, we can say any current carrying conductor behaves as a magnet, and that the magnetic properties are produced in that magnet. So now we can say that the current has a property that it can produce magnetic effects in the conductor. So this effect has a great importance, a great application in today's life. We can say this effect can be used in many ways, in many devices where we use this effect. Like electric motor, we use this effect. We use this chemical effects, magnetic effects of current. So it has a great importance, this effect. So permanent magnet we have discussed. Now the magnet which is produced by flowing electric current, that magnet we call as electromagnet. That means that magnet is produced by flowing electric current. So if we discuss, like for example, we take an example of a bar magnet here. Before we discuss the further this, how the Hans Christian Ørsted has discovered this effect, what are the consequences, what are the activities at that time by which he has obtained this such type of magnetic effects of current, has discovered. So before we discuss what is magnetic field and magnetic lines of force. So if we take a bar magnet, and this bar magnet, around this bar magnet there is a region, there is an influence around this bar magnet under which it attracts or repels other magnets. For example, if we bring another magnet or magnetic material towards this bar magnet, what will happen to that other magnet or magnetic material? That will either attract that material, or if we bring the same like pole of the magnet towards the south, like south of the one magnet and south of the other magnet, they will repel. If we bring the north of another magnet towards the south of this magnet, they will attract. So this influence, this zone, this region around this bar magnet under which it attracts or repels other magnets, that we call as magnetic field. Let this dotted line represents the magnetic field of this bar magnet. If we bring any magnet which is outside this dotted line, then there will be no effect of this bar magnet on that magnet, because that magnet is beyond its magnetic field. Rather, we can say, if we take, for example, if we take an iron nail, if we take a nail, this is what we call it as, this is magnetic material. If this magnetic material is out of this field, out of this dotted line which represents the magnetic field of this magnet, then there will be no effect of the nail on this. There will be no effect of magnet on this nail. So this dotted line represents the magnetic field of this magnet. When anything which is bring inside this magnetic field, then the magnet has a capability, the magnet has a potential, it will attract this magnet or it will repel it. And this zone, this influence, we call as magnetic field of this magnet. Magnetic field. So this is called the magnetic field. So what is the magnetic field now? Magnetic field is a region or a zone around a magnet under which it attracts or repels other magnets. So here the dotted line represents the magnetic field, for example, of this magnet. So this magnet can attract or repels the other magnets from this point, and outside this point there will be no influence of this magnet. So what basically this magnetic field is, and how this magnetic field is represented. What is basically inside this zone that the other magnets are repelled or attracted, or this force is applied on this magnet. So for that we have to do an activity, one important activity. For example, if we take certain points like point A, point B, point C, point D, point E, and point F. These are few points around the bar magnet. Now place the compass at point A. You know, compass is a tiny magnet, and compass has a needle like this, and this needle is basically a tiny magnet. It has its north pole and south pole. So compass is basically a tiny magnet. The compass needle has a tiny magnet. When we place this compass at point A, the needle of the compass is freely rotating, because you know the property of a magnet. When magnet is suspended freely, it always rests in a north-south direction. So when we place freely it at point A, we find that the needle of the magnet represents like this. The north pole of this magnet the south pole of this magnet goes towards north of the magnet, and the north will go its opposite side. So when we take this needle here, we find that the north pole of the magnet moves slowly towards the south pole, and the needle will place like this. This is the north and this is south. And when we reach at point C, we find that this needle, the north pole goes down towards the south, because north and south will attract, and south will move towards the opposite side. Similarly, on the lower side, we see at point D, the south portion will be towards north, and north will be in opposite direction. And when we bring it at point E, we find the north will move towards the south. This is north and this is south. And at point F, we find the north is completely towards the south, and south is in the opposite direction. If we find the direction of these needles, if we see clearly these needles, we find that the north direction, we find that these needles form a continuous curved lines which are arised from north and moves and towards and set the south. Similarly, at down, we find that these needles are obtained. These needles are joined to form the curved lines which are arised from north and ends at south. It indicates that by these directions of the magnetic needles, we find that there are certain continuous curved lines which are arised from north, which appears to arise from north and ends at south, below as well as above as well as. So if we see above, they are also obtained from north to south. Below, they are also obtained from north to south. So these lines, these curved lines, are arised from north to south. And these curved lines, which are arised from north to south, north and ends at south, these are called as magnetic lines of force. Lines of force. Magnetic lines of force or magnetic field lines. So we can say the magnetic field of a magnet are represented by imaginary continuous curved lines which are arised from north to and ends at south. These imaginary curved lines represents the magnetic field of a magnet. So if we see these magnetic lines of force, these are curved, these are imaginary. As such, we never find such. If we place a magnet there and if we see its magnetic field, we doesn't never find any curved line. So these are imaginary. These are obtained when we place the compass at different points and we find that certain curved lines are appearing. Curved lines are joined when we join the directions of the needle. And these curved lines we call as magnetic lines of force. So we can say that the magnetic field or magnetic field of any magnet is basically composed of these imaginary continuous curved lines, which we call as magnetic lines of force. Let us discuss these magnetic lines of force and their properties. Okay, so magnetic field lines and their properties. So magnetic field lines. Now you got an idea that what are the magnetic lines of force or magnetic field lines. So these are continuous. So these are curves, continuous, these are curved continuous lines which represents magnetic field. Field of a magnet. a magnet. So these are curved continuous lines which represents magnetic field of a magnet. So what are their properties? You know, these curved lines has a first important property that they are imaginary continuous curved lines. So these are imaginary continuous curved lines. Number second, so like I will represent here, this is a bar magnet. So these are continuous curved lines, continuous imaginary curved lines. And the second property, if we see clearly the picture, clearly the diagram, you see that these curved lines are arised from, so far the direction is concerned, they are arised from outside the magnet. They are arised from north to south. So we can say outside the magnet, they are directed from north to south. They are directed or they are arised from north and ends at south. But if we see inside the magnet, these magnetic lines of force are directed from south to north, like this. The direction is from north to south to. So here clearly it indicates that these lines, these curved lines are arised from north and ends at south. But if we see inside the magnet, these magnetic lines of force are directed from south to north. So it is clear that these magnetic lines of force has two important directions, outside the magnet and inside the magnet. Outside the magnet they are north to south, and inside the magnet they are directed from south to north. One important issue is here, one important point is here, as per these magnetic lines of forces are concerned, if we see outside the magnetic lines of force, the magnetic lines of force which represents the magnetic field outside the magnet, it is always non-uniform. It is always non-uniform. What does it mean non-uniform? That means if we see the direction and magnitude of this magnetic field at any point outside the magnet, that is different. At every point, the magnetic field of a magnet outside the magnet is different. For example, we take the point A here. I want to find out the direction of this magnetic field at this point. You see, the magnetic field at this point is at drawing a tangent at that point. We find the magnetic field direction at any point by drawing a tangent. So when we draw a tangent, we find that at point A, that this is the direction of magnetic field. And if we compare this point A with the point B, and here if we draw a tangent, we find that the direction of this magnetic field is different from point A. So the magnetic field direction or the magnitude, or rather we can say the magnetic field strength at any point outside the magnet is different. So outside magnetic field represented by the magnetic lines of force, they always represent the non-uniform magnetic field. So outside the magnetic field is non-uniform, but if we see the inside, these magnetic lines of forces are directed from south to north, and these magnetic lines of force are equidistant. That means they are equidistant, having every line has equal distances together each other, and they are directed one particular direction from south to north. So these magnetic lines of force represent magnetic field inside the magnet as uniform magnetic field. Uniform magnetic field. I will repeat this point. You know that the magnetic field lines outside are north to south directed, and if these magnetic lines of force which make the magnetic field outside, this magnetic field is always non-uniform, because at every point the magnetic field direction and magnitude will be different. But if we see inside, these magnetic lines of force are moving in one particular direction. All the magnetic lines of force inside a magnet are moving in one direction, that is south to north, and they are equidistant to each other. That means at each and every point inside the magnetic field line strength and their magnitude, their direction will be same. So we call that magnetic field as uniform magnetic field. Now there is a simple question. If anybody asks you that what is a uniform magnetic field of any point, so you can say that a magnetic field of a magnet at any point is said to be uniform when their magnetic lines of force are moving in one particular direction and are equidistant to each other. That means at the point, any point where the magnetic lines of force are moving in one direction, in a one particular direction, and all these magnetic lines of force are moving in one particular direction, and the distance between them are equal and equidistant. They are equidistant moving, and we can say at that point the magnetic field is uniform. So this is why we can say that the uniform magnetic field of a point is uniform when the magnetic lines of force of that point on that region are moving in one direction and are equidistant to each other. So here we got an idea now. Outside the magnetic field is non-uniform. It is non-uniform. But if we see inside the magnetic field is uniform. Okay, now the third important property that we have discussed, that is a very important property. Please, this property is very important. If we see the magnetic field strength of this magnet, see these magnetic lines of force are very close, where at the poles. So here, because these at the poles they are coming out, and at the south pole they are entering inside the magnet. So at these poles, these magnetic lines of force are very close to each other. So this closeness gives the magnetic strength of the magnetic field. If we see here, they are very close. When they come out, these magnetic lines of forces are moving apart from each other. That means they are moving apart from, they create a distance between them, a larger distances between them. So the distance between two magnetic lines of force basically gives the magnetic strength of that magnet. So we can say the strength of magnetic field of a region is determined by the closeness of these field lines. So what does it mean? These field lines are so very close in the bar magnet, they are very close at poles. So we can say in the bar magnet, the maximum strength, magnetic field strength is at its poles. Because at the poles, they are so close to each other, so the magnetic field is very high. But when they come out at the peripheries, these magnetic lines of force are moving apart from each other, creating distance. They are moving apart from each other. So we can say the magnetic field strength outside the magnet is very low. But at the poles, the highest magnetic strength of the bar magnet is felt. Where? At the poles of the magnets. Because this property indicates that the magnetic field strength is basically determined by the closeness of these magnetic lines of force. Now, So closeness of these magnetic lines of force gives the magnetic strength. So tell me one thing important. If we see the inside these magnetic lines of force, these magnetic lines of force are moving from south to north. They have a one direction, and these magnetic lines of force are equidistant to each other. So there is equal distances at each and every point. So we can say inside the magnetic field is uniform. There will be no increase or decrease in the magnetic field inside the magnet, because these magnetic lines of forces have a uniform magnetic field because they are equidistant to each other. So the closeness of magnetic lines of force gives the strength of magnetic field of a region. Okay. Now another important property, that is very important property. These magnetic lines of force which are arising from north and enters at south, they never intersect each other. That means two magnetic lines of forces never intersect each other. Why? If they intersect, what will happen at that point? For example, if they intersect at any point, for example, this is one magnetic lines of force A, and this is second magnetic lines of force B. Let these two magnetic lines of force intersect at point X. So at point X, they are intersecting each other. This point is the point of intersection. Let this is the condition. The property is that two magnetic lines of force never intersect each other. But if they intersect, what will happen? What if they intersect at point A? Let's consider this point A is the point of intersection where two magnetic lines of force intersect each other. Then what happens? If we draw a tangent at that point of intersection, we find there are two possible tangents. That means there are two possible directions. Is it possible that in any point of the magnetic field there are two possible directions? No. So there is no possibility that the magnetic field direction at any point has two different directions. No, that is completely impossible. So this is why two magnetic lines of force never intersect each other. So another property is that two magnetic lines of force never intersects each other. Now, dear students, if the question is arised, why two magnetic lines of force cannot intersect each other, then the answer will be, if they intersect each other, then at the point of intersection, there are two possible directions, which is quite impossible in the magnetic field. So, dear students, if the question arises, why two magnetic lines of force never intersect each other, then the answer will be that if two magnetic lines of force intersects at any point, that at the point of that intersection there are two possible tangents. That means there are two possible directions at that point, and which is quite impossible in the magnetic field. Okay, this was about the magnetic field lines and its properties. Thank you very much. See you in the next class.